Welcome. In this video we'll be talking about quadratic functions. So first of all, to understand what a quadratic function is, we simply need to realize that what we're talking about here is simply any function that is a transformation of the function f of x equals x squared. So this is our definition for quadratic functions. So f of x equals x squared, this is one of our toolkit functions that we talked about in previous sections. So of course we should make sure we remember how to graph this. So remember, it's just an ordinary parabola is what we call the shape there. So it goes through the points 0, 0, 1, 1, and negative 1, 1, 2, 4, and negative 2, 4. And graphing these points together, we get the familiar shape of a parabola. And so we've seen how to do transformations of these functions in the past, so quadratic functions are actually not new to us. So as an example, suppose we had the function f of x is equal to negative, say x minus 1 squared plus 2. Well, we just want to remember what the transformations are that we're applying here. So recall that the negative that we see in front of the graph, that's going to cause a reflection across the x-axis, or we can just think of it as flipping the graph upside down. The minus 1 that we have inside the parentheses, that tells us to shift to the right 1 unit. And the plus 2 on the outside here, that's going to tell us to shift up 2. And so taking all of that into account when we want to graph the function here, let's see what we have. Well, shifting to the right 1 and up 2, that would take us to the point 1, 2 here. And then we said that the parabola will be flipped upside down, so our graph should look like this. Also, don't forget that we can find the domain and range of this function once we know what the graph looks like. So recall that the domain for x squared is all real numbers, negative infinity to infinity. In this graph, our range, again going from bottom to top, would be from negative infinity up to and including 2. So the 2 does need to have a bracket on it. So these are transformations that we saw in previous sections. There will be a new transformation that we had not seen before. And as an example of this, let's compare the function f of x equals x squared to, let's say, g of x is equal to 2x squared. So I'll go ahead and graph these on the same set of axes. So x squared again, saw this a moment ago, and of course we should already have this memorized. Oops. But our graph looks something like this. Well, if I were to look at the graph of 2x squared, what would happen there? If I were to plug in 0, I would still get 0, but notice that if we plug in 1, we would get 2, and same thing if we plug in negative 1. And if I were to plug in 2, I would end up getting 8, which would be way up off my grid here somewhere. But what ends up happening is we end up with a parabola still, but notice that it is narrower. We say that it has been stretched vertically by a factor of 2. And that happens because of the 2 that we're multiplying by the x squared. On the other hand, what if we were multiplying by a small number, like 1/2? So let's look at a third example here. Let's say h of x is equal to 1/2 x squared. What does the graph of that look like? Well, in this case, since we're multiplying each of the y values by 1/2 now, if I were to look at when x is equal to 1, we would get 1/2. Same thing with negative 1. If I were to plug in 2 there, I would end up getting 2. Same thing if I plug in negative 2. And so once again, we still have a parabola here, but it is widened. Or another way we can think of that is to say that it has been compressed vertically. And so what happens here is that when we have some value that's being multiplied by the x squared term, it will either cause the parabola to become more narrow if the value is larger than 1, but it'll cause the parabola to become wider if the value is less than 1. So as another example here, let's try combining this together with the other transformations that we know about. Suppose I wanted to graph the function, let's say f of x is equal to negative 2 times x plus 3 squared plus 1. So what's happening this time? Well, the negative that we see in front, that would still flip the graph upside down. However, because the number in front of the x squared factor here is 2, which is larger than 1, that means that this is going to be a narrow parabola. The other transformations, though, are still the same. So the plus 3 inside here, we know that that would shift the graph to the left 3. And the plus 1 at the end, that's going to shift the graph up 1. So there's 4 different things going on here. So again, the negative in front is just reflecting it upside down. The 2 that we have there makes the parabola narrow. The plus 3 on the inside is shifting it to the left 3, and then we're also shifting it up 1. So let's put all this together in order to sketch our graph. So we can see that our graph will start at the point -3, 1. And then, as we said, it'll be upside down and narrow. So I would see a graph that would look something like this. So we have this new transformation for when we have this number in front of the parentheses containing the x squared term, and how that affects the overall shape of the graph. So again, if it's positive, that would mean that the parabola would open up. If it's negative, as we see here, it opens down. And then the number itself tells us whether the parabola will be wide or narrow. If it's a number like 2 or anything larger than 1, like we see here, we'll have a narrow graph. If it's something like 1/2 or 1/3 or some fraction that's less than 1, then it will be wide. Well, in general, this expression here is what's called the standard form of a quadratic function. And some textbooks describe this as the vertex form instead. But what we write here is f of x is equal to a times the quantity x minus h squared plus k. So the h and k values, those are going to tell us the vertex. That's the turning point of the parabola. And that just comes from shifting the graph left and right and up and down like we've seen before. So identifying the vertex should always be fairly simple. If a is greater than 0, like we mentioned, the parabola opens up. If it's less than 0, it opens down. And what we've learned in this video is that if the absolute value of a is greater than 1, then the parabola is narrow. But if the absolute value of a is less than 1, the parabola is wide. And we use absolute value here because a itself can be positive or negative, which just flips the graph either upward or downward. But it's the number itself, whether that's greater than or less than 1, which tells us whether the parabola will be narrow or wide. So let's try one more example of using this vertex form or standard form of the quadratic function. So let's look at the example of f of x is equal to, let's try -1/3 times x plus 1 squared minus 2. Well, again, let's identify everything that's happening here. So we see that we have a negative in front, which once again means that we'll have an upside down parabola. But now the number that we see in front there is 1/3, which is less than 1, so we'll see a wide parabola in this case. Then the plus 1 on the inside, that shifts it to the left 1 unit. And of course the minus 2 on the outside here means that we will shift it down 2. And so again, let's put all this together in order to sketch our graph. So we'll come over here to -1, -2. That's where the vertex will be located. And then we're going to see a wide parabola that opens downward like this. And so this is what our graph would end up looking like. And again, when we are graphing these functions, they're always just sketches of the graph. They don't need to be absolutely perfect. So when you are graphing these functions, don't concern yourself too much with just how wide or how narrow you make the graph look. You can feel free to exaggerate those features if you want, just to make sure it's clear what you're drawing. But they are just sketches of the graphs. They don't need to be absolutely perfect. Just make sure you know how each of the parts of the function will ultimately end up affecting the graph every time. Well, another thing I want to mention here are the coordinates of the vertex. Many of the problems in this section will ask you to identify those. So as we stated before, we usually label them by the values h and k. And so here we can see that the coordinates of the vertex are simply -1, -2. Notice that you can also determine this just by looking at the equation itself. But for the h value, the x coordinate, in other words, you're looking inside the parentheses. So in this example, we'd be looking at the x plus 1 that we are squaring in the original function. And notice that the plus 1 turns into a -1 when we find the x coordinate there. And that will always happen. You'll always end up changing the sign of that value. when you're trying to determine what the actual coordinates are. The k value just comes from the -2 that we see on the outside, and that number we never have to change. It will just stay as is. But the h value, the x coordinate, just comes from the inside of the parentheses, and you just need to remember to flip the sign there. Well, next let's take a look at the general form of quadratic functions. So the example we're looking at here is when we have an equation that looks like ax squared plus bx plus c. Well, if I want to graph this type of function, it's going to be easier to work with if we think of it as being in the standard form, or the vertex form, the a times x minus h squared plus k. Well, the first thing I want to mention here is that the a values that we see in each of these expressions are the same. So if the a value in the first equation there is equal to 2, let's say, then it would still be equal to 2 when we're looking at it in the standard form or vertex form. And either way, it would indicate that we have a parabola that would be opening upward and would be narrow. But if we're going to graph an equation of this form, we want to know what it looks like in the vertex form, because that will be a lot more useful for graphing purposes. And so what we can determine here, and doing this actually requires using the quadratic formula, but it can be shown that for the vertex of the first equation, to find the x coordinate, you simply have to set x equal to -b divided by 2a. And so that would end up giving our h value for the vertex. For the y coordinate, we simply have to take whatever the -b over 2a value is and plug it back into the function. So we have to find f of -b over 2a. And that will give us the k value every time. So when we're trying to find the coordinates of the vertex using the form ax squared plus bx plus c, we can simply follow this process every single time. So let's take a look at some examples of how this works. Suppose I wanted to graph the function. Let's say f of x is equal to 2x squared plus 8x plus 5. Well, trying to graph it directly from this form wouldn't be very simple. So we want to put it in the vertex form, or the standard form as it's also called. And as I just mentioned, to do that, we'll first set x equal to -b over 2a. So in this case, -b, that would be -8. 2 times a would just be 2 times 2. So we would have -8 over 4, which ends up being -2. And so that is the x coordinate of my vertex, so I can also think of that as just representing the h value. For the y coordinate, we simply have to take that number now and plug it back into the function. So we have to find f of -2. So in this example, that becomes 2 times -2 squared plus 8 times -2 plus 5. And so simplifying here, we'll have 2 times 4 minus 16 plus 5. So that's 8 minus 16 plus 5. If you add all those together, you should end up getting -3. So our vertex here, again writing it in the form h comma k, is simply -2, -3. Notice that we also were able to determine that our a value is equal to 2. And so what that means is that this parabola is going to be narrow and it will open upward. So that gives us everything that we need to be able to graph the parabola itself. So let's go ahead and do that. So our vertex in this case we said is -2, -3. And then as we pointed out, it would be a narrow parabola opening upward. So I would see a graph that looks something like this. So that would be the sketch of our graph, and so we just have to use these formulas here for finding the h and k values, the x and y coordinates of the vertex. Once we know that, and we also know the value of a given in the original equation, then we can always produce a sketch of the graph. So let's try another example like this. How about if I have the function f of x is equal to, let's say, -1/2 x squared plus 2x plus 3. Well, again, we'll graph this function, and so the first thing that we'll need to do is to find the vertex. So again, setting x equal to -b over 2a, we'll have -2 over 2 times -1. So this becomes -2 over -1, which of course is just +2. Again, to find the y coordinate, we simply have to take that number that we got for x and plug it back into the function. So this becomes negative 1/2 times 2 squared plus 2 times 2 plus 3. Of course, that'll simplify to negative 1/2 times 4 plus 3. So we have negative 2 plus 4 plus 3. And of course, that will be 5. So the coordinates for our vertex, if I want to write them as h and k, we can see that they would be at 2, 5. And in this case, our a value, if we go back and look at the original function, is just negative 1/2. And so again, what that means is that this would be a wide parabola that opens down. And so again, this gives me enough information to be able to sketch the graph of the function. So let's go ahead and do that. So starting from the point 2, 5 here, that's where our vertex is. We just want to see a wide parabola that opens downwards. So the graph would look something like this. Let's try one more example like this. Let's take a look at the function f of x is equal to negative 1/2 x squared plus 1/2. Well, when we see a function like this, we don't necessarily have to use the negative b over 2a formula to find the vertex, although we could. Instead, what I'm going to do here is I'm going to think of the x squared as being the same thing as x minus 0 squared plus 1/2. So what we want to notice here is that we wouldn't be shifting the graph left or right anywhere because we're just subtracting 0 from the x term in this form. So really what's going to happen here, if we were to look at the vertex of this parabola, we should be able to see that the h and k values would be 0, 1/2. And basically that amounts to just shifting the graph up half a unit. Our a value, though, is negative 1/2, which again means that we would have a wide parabola that opens downward. So again, we can use this to sketch our graph. Let's go ahead and do that. So as we mentioned, the vertex would be at 0, 1/2. So I'll just kind of estimate that, just putting it halfway between 0 and 1. And again, we would have a wide parabola that opens downwards. So the graph would look something like this. Again, it does not need to be a perfect sketch. I'm just looking for a pretty good estimate. But the key thing to realize here is that when you have just an x squared term and it's not followed by an x term, just think of that as being x minus 0 squared. So you can go straight to writing it in the vertex form, identify the coordinates of the vertex, and go from there. Well, when we're working with quadratic functions, one of the most important aspects of them is doing applications. And specifically, we'll be looking at applications involving maximum and minimum values. So it's possible when you're dealing with a quadratic function to find a maximum or a minimum of that function. The way this works is just from understanding the functions themselves. So when I have a quadratic function, if the parabola is opening upward, well, we know that occurs when the a value is greater than 0. But what I want to point out here is that in this case, when we look at the coordinates of the vertex, it's the lowest most point on the graph. So in this case, the vertex gives us a minimum value. It's the lowest point on the graph, so it would give us the smallest y value of the function. On the other hand, if we see a parabola that opens downward, well, we know that that occurs when the a value is less than 0. But in that case, the vertex is located at the top of the graph. And what that means is that the vertex is giving us a maximum. And so in common applications of quadratic functions, they'll ask you to determine the maximum or minimum value of the function. And really what that boils down to is just determining the coordinates of the vertex. So let's go ahead and take a look at a couple of examples of how this sort of thing works. So to start off, let's look at how we could maximize the profit for an auto manufacturer. So in the problem here, we have that the profit for an auto manufacturer can be modeled by this function here. P of x is equal to negative 10x squared plus 3,500x minus 66,000. So here, P of x represents the profit in dollars when x vehicles are sold. So the question is actually broken into two parts. First of all, how many vehicles should be produced to maximize the profit? And secondly, what is the maximum profit? Well, again, if we're trying to find a maximum value here, we really just want to find the coordinates of the vertex. And it should make sense that we would be finding a maximum here, because notice the a value is -10, which means that if we were to graph the parabola, it would be opening downward. And sure enough, the vertex would be a maximum number. Well, to find the vertex, we again just stick with the formula x equals -b/2a. And so in this example, that would become -3,500 over 2 times -10. And so simplifying this, we should end up getting 175. Now, what exactly does that represent? Well, it tells us in the problem. Notice that it says that X vehicles are being sold. So the X here represents the number of vehicles that we're talking about. So what we've just determined here is that in order to maximize the profit, we want to sell 175 vehicles. So that answers the first part of the question. The second part, what is the maximum profit? Well, for that, we simply need to take this number and plug it back in. So we need to find P of 175. So it would become -10 times 175 squared plus 3,500 times 175 minus 66,000. And so obviously when the numbers start to get really big like this, using a calculator will be very handy. What we end up getting is 240,250. And here the profit is being measured in dollars, so we just want to indicate that this is a dollar amount. So by selling 175 vehicles, this auto manufacturer produces a maximum profit of $240,250. And so it's just as simple as determining the coordinates of the vertex, which again just relies on using the fact that x is always going to be equal to -b/2a. And so we do the same sort of thing if we're trying to solve a minimum application. So let's look at an example like that. What happens if we're trying to minimize some function? Well, in the example that we'll look at here, we're going to look at minimizing daily production costs. So in this example, a cell phone manufacturer has daily production costs that can be modeled by this quadratic function, c of x equals 1.6x squared minus 240x plus 15,000. So here, c of x is the daily cost in dollars, and x represents the number of cell phones produced in hundreds. So before I go further here, I do want to point out that the problem says in hundreds. So what that means is that every x value that we get here would actually represent 100 cell phones. So for instance, if we had x equals 1, that would actually represent 100 cell phones, not just one cell phone. So that's what that in hundreds represents. And sometimes problems will contain language like that. So you want to make sure you understand what that means. Anyway, this question is also split into two parts. First of all, how many phones should be produced to minimize the daily cost? And also, what is the minimum daily cost? So even though they're asking us to find a minimum rather than a maximum, the process is still the same. We're still simply looking for the vertex. And it should make sense that the vertex is giving us a minimum because our a value in this case is 1.6, which is positive. That means that the parabola would open upward if we graph it. And so the vertex is the lowest point. It's the minimum value that we're looking for. Well, at any rate, let's go ahead and plug in our numbers to the formula. So x equals -b/2a. In this case, that would become positive 240 over 2 times 1.6. And so going ahead and dividing this, we should end up getting 75. So notice that what this means is that we want this to represent 7,500 cell phones. That's how many are actually being produced here. So again, the x value is represented in hundreds. So we're talking about 7,500 cell phones, not just 75. However, to figure out what the actual minimum cost will be, we want to find C of 75. So even though that 75 represents 7,500 cell phones, the actual x value itself is what we need to plug back into C here. So doing so, we would end up with 1.6 times 75 squared minus 240 times 75 plus 15,000. And again, you'll want to use a calculator to help you out with the math here, but you should end up getting 6,000 as the result. And again, this represents a dollar amount, so we're talking about $6,000 here as being the minimum daily cost to produce these cell phones. So 7,500 cell phones are the number that we actually want to manufacture. $6,000 ends up representing what the minimum production cost would be.